So this session is about some hints about how to set up the back propagation piece. So last week we discussed the feed-forward part, and that was used in order to set up the dimensionalities or the matrices and vectors which are involved, so that you know what kind of output you should produce. And what we have now, when we look at the back propagation piece, is a network of this type. So we would have the two input nodes. We have two hidden nodes in the hidden layer. And the function, the so-called activation function, is in these cases here given by the sigmoid function, which you have in the bottom here. So this is pretty straightforward. And we have the same function in the output layer here. And the red quantities in the figure, these are the parameters we are going to fit. Now, the thing which is useful to notice now is obviously that the output is now fed into the cost function. And this is where you compare the output with the target values. Now, in your case, if you use the sigmoid function, you produce values between 0 and 1. Now, these values obviously continuous values between 0 and 1, and you would like them to produce binary outputs like 0 and 1. So you would typically put a threshold. If the output is less or equal to 0.5, you put it to 0, and else you put it to 1. And then you would compare that with the target values, which are binary ones as well. Now, the thing to pay attention to now is when you want to move over to use autograd or automatic differentiation. Because the cost function which we have opted for, which is the quantity we would evaluate when we have produced the first output after the feed-forward pass. So we make a feed-forward pass, we produce the output, which is now given by this function here. You see now that the output here depends indirectly on the parameters we need to update. So the weights and the biases are input parameters to the activation function. And when you look at the expression for the cost function, that depends normally only on A, and A depends on Z, which then depends on the weights and the biases. So when you use autograd, what is normally done is that you would apply autograd to the cost function only with respect to the parameter A, the output. So if you now look at the way you would set up the back propagation piece, if you look at that one, what you would have is a derivative of the cost function at the output layer. So L here, the uppercase L is the output. And in this case, you would use the chain rule because you don't have a direct dependence in the cost function on the weights and the biases. So using the chain rule, you take first the derivative here, and this is something you could then either hard code, and in this case, the functions are pretty simple, and you have to make a decision whether you want to hard code it or whether you want to use autograd. So you would use autograd on that function C directly, but with respect to A. So just keep in mind then that when you do that, if you take the derivative of this function here for the cross entropy, you would get something like this. And this is what autograd would give you if you take the derivative. You can obviously, if you're able to spell out an explicit dependence on the weights and the biases, then you could take the derivative directly. But normally that's not the case. So that's why we need the chain rule. And with the chain rule and autograd, then you have to be a little bit careful about what is what and which kind of dependencies you have. So using the chain rule again, you have this intermediate step here, where this one is your output with respect to the input, and that is nothing but the derivative of the activation function. And if you use the sigmoid, this has a very simple mathematical form. So one thing you will notice is that when you use autograd, that can be slower than hard coding the activation functions and the cost function. And the reason for that is that normally when you choose an activation function, you want to catch many birds with just one stone. You want to have a simple mathematical expression. You want to have a continuous function. You want to have a derivative, which is nice and continuous and easy to evaluate. And then you would also like to have something which is meaningful. So if you look at the sigmoid, that has all these properties. So this means often that the derivative has a very simple expression. So this is you striking the balance between the number of cycles you're willing to invest and the accuracy you want to have. So having a function which is as simple as the sigmoid means that sometimes using autograd can lead to an overhead, which means you have the longer run times. But this is where you have to strike the balance between runtime plus development times. So if development time involves setting up gradients and functions which are complicated to evaluate, then development time may be longer. The total time of a project is the sum of development time, testing time plus runtime, which means that if you just save a tiny fraction of time on runtime by using the hard-coded version, and you spend weeks and months on development, clearly using autograd makes it much easier. And also, if you want to automatize it and use many other types of activation functions, it's much easier to actually use autograd then. So this is a balance you guys have to strike, okay? And keep in mind that when you do this now, this function which you see here, this term delta, which I in the codes have called an error, this is given by the product of this derivative and that derivative. And if I use the cross entropy and the sigmoid function, then this actually simplifies to the expression which you see here. So that's a pretty easy case to set up. And then you need to have this one, which is also pretty simple because that is the output from the previous layer. So with these expressions, then you can start stepping backwards to the first hidden layer. And in this specific case, you just have one hidden layer, but the expression which you need to code and which we derived is this one. And that contains the derivative of the activation functions. And at the end, in the example which you will see in the lecture notes in week 42, we are just implementing a plain, simple gradient descent. Nothing but that. Which means that when you are testing and developing your code and you're matching the code and bringing in the gradients you've developed through AdaGrad, root mean square propagation, etc., it's convenient when you to test your code actually to just run it with a simple plain gradient descent. If that functions, you can add momentum. If that functions, you can start adding AdaGrad, root mean square propagation, and the other methods. So these are the kind of steps which are useful to look at when you're setting up your back propagation. Now, one of the things you will notice when you now are setting up things here is that the XOR gate and the OR gate, etc., we have only 4 inputs because we just produce with X1, X2, we produce either 0 and 1, and we have 4 cases. Now, you know that training any of these methods are all data greedy, which means the more data, the better the fit. So what you could do now, since the data will always be the same, is that you can duplicate the data. So you can augment your design matrix by the same data once or twice or 3 times, or you can do it 1,000 times. So instead of have a matrix which is a 4 by 2, you could have a matrix which is a 4,000 by 2. So that would give you more data in the training. So we saw last time that if you tune the hyperparameter and the learning rate, you could get a perfect fit to the output, the target. But that was a case where you had tuned the learning rate and the hyperparameter so that you would get the data. But if you want to train this with a larger set of parameters and get a better result for more parameters, you could actually increase the data set. So let me just bring back that piece in the slides. So when you go back to the exercises, which we had, which we discussed last week in detail, what we have then is a design matrix, which looks like this. Now this contains now the 4 entries. So these are 4 data points, which we have. If you now want to train with more, you could just duplicate this one. So you would have an 8x2 matrix. So 8 entries. You can do 12x2, triplicate, and you can redo this data again and again and again. And that will give you more training data. And often what you will see then, the more data you have, and we saw that in project 1 as well, the more data you gave to the methods, the better the fit. And this is the case here as well. So neural networks and any of these deep learning methods, they are by nature data greedy. So if you then go back to the codes which we had from week 42, so let's bring up the codes from week 42. There is an example code of the backpropagation one, a very simple one. So if we just scroll down to the first backpropagation set, and this is something you could try to look at in case you are in doubt. So there's a feed-forward pass, which we discussed last week, and that serves to set up the dimensionalities. Then if you scroll down, there is a backpropagation piece. So this error output is the same as the delta parameter we had on the whiteboard. So this gives you the delta parameter for the output layer, because now we have a very simple case with the sigmoid function, which cancels the denominator in the derivative of the cost function. And then the error, the total one for the hidden layer, contains then the output parameters from the hidden layer as well. And then having set up these matrices correctly gives you the right dimensionalities immediately. So when you do the feed-forward part, if you set up the matrices wrongly, then these matrices will also have wrong dimensionalities. And then when you have this delta parameter for the output layer and for the hidden layer, so this is just you setting up the equations, then we have the weights for the gradient in the output layer, which is just a plain matrix multiplication. We have a similar one for the bias, and a similar one for the weights in the for the hidden layers, for the weights and the biases, the gradients for biases and weights. And these are again given by simple matrix or multiplication or just a sum here. Because the bias is just given by a vector. And this function returns the different gradients. And here you see now the training. This is a plain brute force planing. There's nothing intelligent here. This is just a gradient descent. And you will also notice that we do this 1,000 times. So 1 time means 1 forward step and 1 backward step. So when you display the results as a function of iterations with neural networks or deep learning methods, 1 iteration is a feed-forward stage and a back propagation part. And you will see now that we do this in a brute force way 1,000 times. Here you could have a test on your classification function or your score, like the mean square error. If that one drops beyond a certain value, you would stop. Here I just let it run 1,000 times without thinking too much. So I leave the thinking to you guys, because you're supposedly much smarter than me. You are actually. And then in this case, I have the regularization, which I included here, but you don't need that in the beginning. So this would just be the plain gradient descent, which is applied to the output layers and the hidden layer. And you see that we have a back propagation, which is called every time. And the back propagation calls the feed forward part. So you do a back propagation, but that needs an output from the last hidden layer and the probability. So you need the output from the hidden layers and the probabilities, which are the quantities you get from the output layer. And this is used to produce the gradients. And then you train your network here in one step, and then you redo these iterations again and again and again. So every iteration is a feed-forward pass and a back propagation pass. That sound reasonable? So I'm going to put up this recording online so you can take a look at it in case you are in doubt. And hopefully that can aid some of you who are still struggling with dimensionalities and how to set up the back propagation part. So try to keep it as simple as possible. And when the plain gradient descent functions, then you can start adding the other methods, which are normally performing better than just plain gradient descent. So you would simply replace what you see here with a stochastic gradient descent, and then you can add momentum, etc., etc.